Thank you, Shi. Thank you to all of the organizers. Let me begin by saying that this talk is not about a specific recent or forthcoming paper of mine, and it's not going to include a lot of new technical material. There will be some, but what I've mostly decided to do is to summarize and comment on a body of work that's been developed over the past few years. I've decided to do this for two reasons. One is that we have a very broad audience here. We have people from sort of all across quantum gravity and high energy theory, and I think there's some really interesting work that's happened in my particular corner of the world, which is semi-classics, algebras, information theory, and I think it's worth trying to diffuse that to the larger audience. But the second reason that I've elected to sort of do this summary and comments talk is because I think that even for those of you who have seen one or two talks on this topic before, I'm going to have some perhaps new perspectives, new connections to draw, hopefully new insights that will make this worth your time. So let's see if I'm right. Specifically, the subject is semi-classical black hole entropy. So the question of the day is, or the question of this talk, not the question of the day, is what can you say about semi-classical black hole entropy without having a microscopic description? And in asking that question, I'm going to insist on the Lorentz signature. That's why this is here in the talk, because I'm not going to let myself use anything like the Euclidean path integral, which seems to have an undue amount of information about microscopics. Let's really talk about spacetime and ask, what does spacetime know? But to start, let's just talk about entropy. This is the 8th talk in an 8-talk day. Let's have a little fun and do something easy. I think it's worth sort of remembering that entropy is a sort of finicky concept that can mean a lot of different things and has meant a lot of different things historically. So maybe we should just take a few minutes to talk about entropy writ large. It's sort of interesting to think about where it comes from. It comes from thermodynamics, as we all know. It comes from this guy Clausius in 1865, who is trying to explain this phenomenon that heat tends to spontaneously move from warmer bodies to cooler ones. And he doesn't have a description of why this happens, but in coming up with an empirical law, he sort of says, well, you can describe this by associating a quantity to sort of thermal processes, which is the amount of heat absorbed by a body divided by its temperature. And he says this thing tends to always go up in situations where heat moves from warmer bodies to cooler ones. And he calls this entropy, which is a combination of a couple of different root words from different languages, meaning the energy of change. So he doesn't have an explanation for what this energy of change is, but it's something that we can think of as sort of describing this phenomenon of heat transfer. Now, of course, in the next 30 or 40 years, Boltzmann and Gibbs come along and they do this amazing thing. They invent statistical mechanics. And when they invent statistical mechanics, they give this entropy that Clausius came up with a microscopic definition. They think about classical mechanical systems that are probabilistically distributed over phase space. And they define this quantity S equals minus integral P log P, where P is that phase space distribution. The reason they do this is because in situations where they can actually compute this quantity, like in the theory of ideal gases, or more generally in canonical ensembles of phase space systems, they find that it reproduces the thing that Clausius's entropy did, and therefore is a good description of this thing they called the energy of change. Now, it's really important to remember that at the level of classical statistical mechanics, there is an additive ambiguity in the entropy. And it basically comes from the fact that you're talking about a probability distribution over phase space, which is something dimensional. And if you change units on phase space, you change not p d lambda that appears out here, but you change the sort of p without the d lambda that appears inside the log, and that adds a universal constant to all of your entropies. Now, of course, from the perspective of classical statistical mechanics, they don't care because they're trying to reproduce this empirical formula that only involves delta s's. But as we know, as we've already been talking about today, there are many contexts in which we do care about absolute entropies. But that comes next. Perhaps the next insight that Boltzmann and Gibbs come up with is that in these microcanonical ensembles, where they focus in on a little bit of piece of phase space, they end up with this formula that we all love, S equals log of volume of phase space, still with the same additive ambiguity. And this tends to be, I think, how many of us think about entropy, not as this more general definition, but as this microcanonical definition, S equals log of the phase space dimension, because we sort of think of these more general ensembles as being built up of a bunch of microcanonical ensembles stacked together. Now, all of this additive ambiguity that people were worried about is fixed when quantum mechanics comes along. And von Neumann makes this observation that all of the previous entropy formulas can be fit in this formula involving density matrices, minus trace rho log rho. And luckily for us, this completely resolves the ambiguity because a density matrix is a probability distribution over Hilbert space, which is dimensionless. It's not a probability distribution over phase space, which was dimensionful. And this ambiguity that we were previously dealing with doesn't show up. Okay, so that's the story of quantum entropy until 15 years later, this guy Claude Shannon independently discovers entropy in another setting where there's no additive ambiguity. He's asking a completely different question. He's trying to figure out how telephone relays talk to each other. He's trying to understand communication theory, and he's trying to model the messages that relays might send to one another using classical probability distributions. And he happens to stumble across this measure, minus some p log p, which again is well defined because he's doing classical probability distributions where there are no dimensions whose units he needs to worry about. And he comes up with this quantity not because he's trying to reproduce any kind of empirical law like the physicists were, but just because he's trying to come up with good quantities that capture the coarse-grained statistical information of a statistical system. This is a very interesting development, I think, for many of us in this room, even though it happened, 80 years ago, because Shannon was just trying to think about the statistics of information, and he wasn't specifically trying to think about this transformation law, he's not really shackled to this particular definition of entropy. And as information theory develops, people start to develop all sorts of other quantities. Here are some symbols that you can stare at, and some papers where these symbols were defined. All sorts of other things that also capture statistical properties of a quantum state that are perhaps more general or more refined or just different than the von Neumann entropy. So part of this talk is going to be a little bit about how some of these quantities can give us insight into how to think about black holes and quantum gravity. That's going to come towards the very end. First, let's just very briefly remember how entropy shows up in black holes in the first place. Well, there's this discovery of the first law of black hole mechanics, that if you perturb, say, a four-dimensional Schwarzschild black hole, you find that its mass changes in a way that is proportional to the surface gravity times the change in the area. This leads you to guess that you should identify surface gravity with temperature and area with entropy up to a constant of proportionality that isn't fixed until Hawking comes along and tells us what the temperature of a black hole is. And that leads us to guess entropy equals area over 4g Newton. And once we go back to our beloved microcanonical statistical mechanics, we guess this formula, log of the degeneracy of states equals a over 4g Newton, which, as Ashok just told us, is confirmed in many concrete microscopic examples. Okay, so that's great. That's a story that, we all know at least the basics of very well and is clearly still, proving very fruitful and is giving us new and interesting physics all the time. But what this talk is about is I want to return to this information theoretic refinement of entropy and remind us that entropy can mean many different things depending on the context. So while a lot of progress has been made in going from this first law of thermodynamics into thinking about entropy as state counting, there's a lot more we could do to think about entropy even at the semi-classical level. And I think there are certain recent developments that make now a really good time to do that because we have tools that we didn't have before. Okay. So for most of this talk, I'm going to be summarizing this work that started in 2021 with this really amazing paper of Witten, then was developed by these authors here, and I'm mostly going to be taking the perspective that was developed in these last two papers by myself, Anthony Speranza, Christian Jensen, Jonah Kudler-Flam, Sam Leuthäuser, and Gautam Satychandran. And the point of these papers was the following. You try to compute a quantum entropy in semi-classical gravity in the most brute force, sort of follow-your-nose way possible. And what you end up finding when you do a principled calculation is that you get a formula that is very suggestive of the Bekenstein-Hawking formula, even though you didn't put Bekenstein-Hawking in as an input. Okay, I'm going to be talking about that a lot and summarizing it for those of you who haven't seen it before, and even for those of you who have seen it before. One thing I want to emphasize is that this calculation is going to be strictly weaker than the microscopic calculations because it's going to give us a notion of entropy difference, not of absolute entropy. But in a way, I think this is sort of like we're filling in the classical statistical mechanics to string theory's quantum statistical mechanics and trying to see what its consequences are. In the sort of second part of the talk, I'm going to tell you about what's called the operational perspective on quantum entropy, which is one way that information theorists think about entropy. And it is basically what I meant when I said there are refinements of the way of thinking about entropy that come from information theory. And here are a couple of papers that have already started bringing this into quantum gravity, and I think a lot more is going to happen in the future. And then finally, I'll close with some preliminary calculations that indicate a connection between these first two things, between these algebraic formulas for semi-classical entropy that were developed over the past few years, and this operational perspective on quantum entropy, which refines it beyond counting states. All right, so that's the outline of the talk. To start, I'm going to take a very bullheaded and literal perspective. I'm going to say that entropy is any quantity of the form minus trace rho log rho. All right, it's going to take some work to interpret such a quantity in terms of the things that we like about physics, but at the very least, let's think about the settings in which we can hope to compute such a thing. In order to be able to compute minus trace rho log rho, we need a setting where we have a trace, duh, and we need a setting where we have a positive operator with finite trace, so that we can have something like a density matrix and we can try to compute this expression. This mathematician, Siegel, in 1960, was, I think, the first person to point out that you could just try to compute this in a lot of settings, even when you don't necessarily have a physical interpretation for it. So the setting in which we're going to be able to compute this kind of formula generally is the setting of von Neumann algebras. The details of von Neumann algebras are not at all going to be important for this talk. I know some people get kind of scared. John Preskill said they make his palms sweat, I think, during It from Qubit last year. Hopefully that doesn't happen here. The point is going to be that in any quantum system with a Hilbert space, you can associate algebras of operators to sets of degrees of freedom. So if you have any sort of big Hilbert space and you have some subset of degrees of freedom, you can talk about the operators acting on that Hilbert space, and then you complete this set in some particular nice limit, some nice topology. That's what we call a von Neumann algebra. The details of the topology aren't important. And what we're going to say is when we have a von Neumann algebra, we're going to declare that the algebra contains density matrices. That's the setting in which we're going to be able to talk about entropy, whenever there's some positive operator with unit trace. This is a bad definition, though, because some algebras can fail to have density matrices for really silly reasons. Think, for example, about the Hilbert space of two harmonic oscillators, okay? And think about the algebra describing all of the operators that act on the first harmonic oscillator. That's going to be an arbitrary operator acting on the first simple harmonic oscillator, tensor the identity on the second. Nothing in this algebra has trace 1, because nothing in this algebra has finite trace, because there's this big infinite dimensional identity hanging around. I bring up this example to make the point that when we think about general quantum settings in which we can talk about formulas like minus trace rho log rho, we should always allow ourselves to use some renormalized notion of the trace. So in particular, in this example, we would use the trace just on the first factor, rather than the first Hilbert space trace, in order to renormalize away that infinity and get finite, well-defined answers. Okay, so this is something that many of you have seen before, but for those of you who haven't, I will say that when you think about von Neumann algebras in this setting, roughly speaking, they get organized into 3 categories. And they get organized into 3 categories depending on whether and how you're allowed to talk about density matrices and entropies. The worst kind is this type 3, where there's no consistent renormalized trace. An okay kind is this type 2, where there's a family of consistent renormalized traces, but they're related by scaling. So you have sort of a whole family of good traces for defining density matrices that are renormalized and they're very well behaved, but you can't actually fix the overall scaling. And then type 1 is the case that we're most familiar with. There is a preferred consistent renormalized trace, for example, the Hilbert space trace. Okay, and corresponding to this are 3 different notions of entropy. In type 3, you have no trace, so entropy can't be defined. In type 2, you have an ambiguous trace, which lets entropy be defined up to an additive ambiguity, so entropy differences can be defined. And in type 1, absolute entropies can be defined. So one thing I want to emphasize is that the difference between type 2 and type 1 is really just the difference between classical and quantum statistical mechanics. The type 2 setting is the setting where you can talk about entropy differences, but not absolute entropies. And part of this work that's been done is showing that these type 2 algebras show up very naturally in the setting of studying quantum black holes. Okay. Yes?
So for 20 years before people started talking about von Neumann algebras, they were calculating entropies in type 3 algebras. What were they doing?
Good. Yeah, absolutely. So you're talking about like getting formulas like C over 3 log L over epsilon for CFT. Right? Okay, so they're getting entropies with a good and preferred choice of UV regulator. Right? So you get something that depends on like log L over epsilon in that case. Therefore, you have some sort of canonical and nice and preferred way of going to a type 1 algebra, or going to a lattice for a CFT in a particular way, and talking about how the entropy scales with the lattice spacing.
It seems at least entropy differences seem to make sense there.
In those settings, not always. I mean, in cases that we know, right? For example, like the nice formulas that are like C over 3 log L over epsilon, then if you have a universal log 1 over epsilon divergence, then you can like compute entropies and take the limit. But these are things that can, in principle, depend on how you regulate. Even the differences can depend on how you regulate. And one way of actually thinking about what this whole cross-product story does is it gives you a way of regulating that gives you, that takes gravity into account, and therefore gives you an entropy difference that is different from the naive one that you compute on the lattice. So yes, there's an obvious thing to do, and it gives you a nice answer, and you can use it to, and people have used it to great success in condensed matter theory, for example, to quantify phases of matter and things like this. But there is nevertheless not a canonical thing to do. Okay. So now I will, for the next 5 minutes, review this work on so-called gravity and the cross product, where what you do is you try to apply these considerations, these algebraic settings in which you have these, entropy differences or absolute entropies or whatever, and you try to apply it very naively to semi-classical gravity. So you consider the algebra of quantum fields in the exterior of a black hole. So you have some fixed black hole background, say eternal Schwarzschild and asymptotically flat spacetime like I've drawn here, and you think about the algebra of all the stuff that sits outside the black hole. Now that's just quantum field theory and curved spacetime. When you try to quantize gravity, you need to quantize all of the fluctuations of the gravitational field. You need to quantize the gravitons on this background. I don't know how to do that. It's very hard in general, very hard to do very carefully. But one thing that you can do, at least to try to get a sense of what's going on, is to quantize a single gravitational mode, which is just the black hole mass. So you say that the metric is going to fluctuate, but I'm not going to be able to keep track of all the fluctuations. I'm just going to keep track of the mass of the black hole as a quantum degree of freedom, and I'm going to see what happens. When you do this, you end up defining a natural semi-classical Hilbert space, which is the Hilbert space of the QFT, tensor, some new wave function Hilbert space, which is just going to be the wave function of the mass fluctuation. And what's the algebra acting on this thing? Well, it's the algebra that you started with the QFT, and then it's all the stuff that acts on the second factor. So this is the operator that encodes the fluctuation in the ADM Hamiltonian, and the conjugate operator. These are like the position and momentum operators for this L2 of R. Okay, so this is what you call the unconstrained algebra, because the reality is that when I couple quantum field theory to gravity, there's a non-trivial relationship between the matter content of the quantum fields and the fluctuation of the black hole mass. That comes in through Einstein's equations, and it enforces a constraint. It enforces that this fluctuation of the ADM mass has to be proportional to some particular integral of the QFT stress tensor. And, at the algebraic level, what that means is that not all of these are going to be good operators, even in the semi-classical quantum gravity theory, because some of them are going to think that the stress tensor and the mass are independent. So the right thing to do if you want to study this theory is to restrict to the subalgebra commuting with this particular combination of these operators. Okay. When you do this, and this is, I think, the really amazing observation that Witten made in 2021, is that you can go to this operator algebras literature, this very fancy stuff, and you can look up what's called Takasaki's duality theorem. Now, Takasaki defined exactly this subalgebra. He wasn't talking about QFT, but he was talking about the same mathematical structure. He defined exactly this subalgebra, this stuff commuting with a constraint, and he called it a cross product. And he proved something very interesting about this cross product. Ignore this first line. It's technical. I'll explain it in a second. The point is that there are some settings, some set of conditions you can put under which this cross product is going to end up being one of these type 2 algebras, in which these entropies are uniquely well defined. Okay, so what are the conditions you actually need to apply this theorem? One is a silly little technical condition. You need this algebra to be a so-called type 3-1 algebra. I told you about these type 3 algebras. Type 3-1 is some subtype. Luckily, there is a whole body of literature indicating that this happens quite generically in quantum field theories, so we're not going to talk about it now, but if you're curious to ask me more questions later, I'm happy to answer them. The other condition you need is that this integral of the stress tensor that showed up in Einstein's equations, or in the component of Einstein's equations that affects the ADM mass, this integral of the stress tensor needs to be the so-called modular Hamiltonian of the state. That's a subtle point. Some of you might not even have seen the words modular Hamiltonian before. I'm not going to discuss this very much. I'm going to tell you, for example, that this is exactly true in the Hartle-Hawking state for a static black hole. In fact, the statement that the Hartle-Hawking state of a static black hole looks thermal with respect to Schwarzschild time is exactly the statement that its modular Hamiltonian is equal to the particular integral of the stress tensor that shows up in the constraint. There's some speculative work, I'm allowed to call it speculative because it's my paper, talking about whether this might be true more generally or might be true enough to work for the purposes of this theorem. But at least, for the general audience, we can say this condition is satisfied for the Hartle-Hawking state in the static black hole. Okay, so Takasaki says if you have these two conditions, then you have one of these type 2 algebras, and even more amazingly, he gives you a formula for its unique up-to-scaling renormalized trace. And what the formula is if you plug in one of these constrained operators, what you're supposed to do is you're supposed to sandwich it with some exponential of the ADM fluctuation, and then you take the expectation value in a particular state. It's this state that was used to define this cross product in the first place. For example, you could think of that as being the Hartle-Hawking state. And then it is the 0 eigenstate of the conjugate variable to the ADM Hamiltonian. Details aren't important. The important thing is that this is something that you can compute with. And what you actually, yes? They are sufficient. Certainly it needs to be, yeah, they are sufficient. I wouldn't have any idea how to have any control over the type otherwise. But you could certainly imagine situations where you cook up some example where you still have this kind of thing. One thing is that I certainly wouldn't expect to have a formula like this, because this formula involves taking an expectation value in this particular nice state. So having a formula that you can compute with, again, this isn't necessary, but I wouldn't know how to do it any other way. Okay. So what do? You want to, within this framework, compute one of these entropy differences. And there's just some rule for doing it, because there's a unique up-to-scaling family of these renormalized traces, and there's really only one thing you could possibly do at the mathematical level. So you... What? Type 3.1 is actually necessary for this theorem. Oh, sorry, not necessary, but it's provably sufficient. I can't say anything else. Oh, sorry, if it were type 1, yeah, certainly. If you take a type 1 algebra and you constrain to a subalgebra commuting with a constraint, it could be many different things depending on the setting. I don't necessarily know. But because the setting we're concerned with is starting from semi-classics, starting from QFT and curved spacetime and trying to do a little bit of gravity quantization, this is the relevant setting anyway. Okay. So you take some state, some QFT state, and some wave function for the ADM fluctuation. And to compute entropy, you need to define what you mean by the density matrix of this state. Well, you define it using the usual formula. The density matrix is the operator that gives you trace of density matrix times some operator in the algebra equals expectation value of that operator. Of course, now we're using our special renormalized trace. And then you appeal to this theorem. I wasn't sure who to cite for this. It's sort of by Edward Nelson. It's also sort of by this guy Sakai. But there's actually a theorem that there is a unique operator row in the constrained algebra satisfying this system. So there's all these great uniqueness theorems that mathematicians came up with, meaning that you could never have done the wrong thing. There's just sort of one thing that you could possibly do when you're trying to compute this quantity. And there is, in fact, a formula for this density matrix. It was computed in this paper with an approximation in this paper exactly, which is some complicated thing. But I just want to point out, again, it doesn't really matter that it's complicated. It just matters that you have an expression that you can compute with. Let me at least point out to you the ingredients that it involves. It involves this integral of t, which was the integral of the QFT stress tensor that showed up in the constraint. It involves this operator theta, which was the conjugate operator to the ADM fluctuation. It involves f, which was the wave function of the ADM fluctuation. It involves the ADM fluctuation operator itself. And the last ingredient it includes is this funny thing, which is called the relative modular operator between phi, the QFT state that we're trying to compute the sort of gravitationally dressed entropy of, and psi, the QFT state that had this nice property that the cross product was defined with respect to. This is some funny QFT thing that encodes sort of the statistical distance in QFT between these two states, phi and psi. And it's something that has all sorts of nice identities that it satisfies and you can manipulate. And if you do some approximations, which aren't going to be important, the approximations let you take the logarithm of this thing and neglect all of the Baker-Campbell-Hausdorff terms. If you do some approximations, you can compute minus trace rho log rho and you get a formula. What's in the formula? There's a relative entropy in quantum field theory. There's an expectation value of the ADM fluctuation. And then there's a term that looks sort of like the classical entropy of the ADM wave function. Okay? Now remember, this is only defined up to an additive constant because of the scaling ambiguity, but it does give us a finite, well-defined formula for entropy differences in this constrained gravitational algebra. Now, it's UV finite if you... Please. You. Yeah, it sort of looks like that, and in fact there was a calculation I did the wrong way the first time because I thought it was that, but there's some extra sort of twisting that happens, and it's kind of funny. Yeah, so but the thing is that this is a QFT quantity, right? And then this f is a wave function that involves a combination of an ADM quantity and a QFT quantity, and that ends up twisting this thing, basically. It dresses the QFT density matrix that you're thinking of. Yeah, and it dresses it in a particular way. Yes, Emil?
Cap is the wave function in this one-dimensional Hilbert space.
Yeah, it's the wave function. You think you have some quantum state that involves some distribution over the black hole mass, right? And f is that wave function. Yeah. Okay. So we had some UV finite quantity. It was involved in terms of some things maybe we didn't exactly know how to compute. But if you put in a regulator, this is a UV finite quantity, that's great. But if you want to compare it to sort of the classic UV infinite things we're used to, we have to put in a regulator. When we do that, we end up with exactly the formula we wanted. A over 4g plus von Neumann entropy of the QFT. These two things are both UV infinite because we take g to 0 and we take the UV cutoff to 0. Plus the entropy of the ADM wave function plus some scheme-dependent infinity. Okay, so that's the work that was done. Maybe some things to point out. This formula was first observed by Chandrasekhar, Longo, Pennington, and Witten. We made this argument in this paper that you could do, they did it for the case of time symmetry. We made this argument in this paper that you could do it even without time symmetry. There was an explicit realization of that in a really nice example in this paper. And then probably the nail in the coffin here is that these people showed that the approximations that we were very reckless with are actually totally well justified. So I think at this point, this formula is kind of unimpeachable. The punchline is that if you couple a QFT to a single gravitational mode and you quantize with constraints, you end up with a natural canonical formula for entropy difference that matches Bekenstein-Hawking. This is tantalizing. I think a lot of us were really excited when we found this. But a lot needs to be done. There are two big questions I'm going to point out. One big question is, why do we get the answer we like from such a simple quantization where we just put in this black hole mass? Really, we're supposed to be sort of quantizing all of the gravitational fluctuations, and you might worry that that's going to ruin the calculation, and this was just an accident of having done something so simple. That might be true. I don't know how to answer that question, so I'm not going to talk about it. What I am going to talk about is another big question, which is, what does this entropy even mean? We computed this very naive formula where we just said we're trying to compute something like trace rho log rho, and we got something that looked like Bekenstein-Hawking at the end, but we want Bekenstein-Hawking to count states or to talk about the statistics of a microscopic theory or something like that. And what we've done so far doesn't tell us that at all. Okay, so that's what I want to spend the rest of the talk on. Is it okay if I do 45 minutes including questions? I mean, because people have already been asking. I don't want to stop suddenly in 5 minutes. Okay. So I want to tell you a little bit about what's called the operational perspective on quantum entropy. Yeah. Yes. Yeah, sorry. So match is maybe strong, like agrees with Bekenstein-Hawking, right? It's a subset of Bekenstein-Hawking, right? It doesn't give you the additive constant. That's very important. Yeah.
Maybe to ask another question.
Yeah.
To what degree is this so surprising? I mean, the QFT, the entropy has this UV divergence. You say you're trying to do something to give a well-defined description for it, and you know.
And you did a well-defined thing, and you got the answer that.
Well, you
yeah.
know that the UV divergence of the entropy QFT scales with the area and gets renormalized in the same way as 1 over G.
Yeah, one thing I would say is that making those arguments, which I certainly believe, does require you to take a lot for granted, whereas here you have to take a lot less for granted. You really just need to do a very mathematically well-defined and uniquely constrained calculation. Yeah. Okay, so as I said, these algebraic methods give us a formula we like, but we have no idea what it means. In fact, something I want to emphasize, because I think we don't think about it enough, is that even in ordinary quantum information theory, entropy is not always something that counts states. As an example, think about a density matrix that has this eigenvalue distribution. It has one very large eigenvalue and a bunch of very small eigenvalues. Its entropy is close to 0, but its rank can be arbitrarily high. So this is a density matrix that's supported on a very large number of microstates, but it has entropy very close to 0. You might say, okay, John, this is kind of a stupid definition, or this is sort of a stupid counterexample to this idea, because these eigenvalues are all so small, and if I throw them away, I get something that's very close to my original state, and its entropy is exactly 0. So in that sense, for this state, entropy is a pretty good measure of rank in some effective sense. This is exactly the consideration that leads us to consider what are called smooth entropies in the quantum information community. So one thing that we might actually care about, rather than the von Neumann entropy, is what's called the max entropy, which is the log of the degeneracy, the log of the rank of a density matrix. But as I just emphasized, this thing can vary pretty discontinuously with an eigenvalue spectrum. So a sort of nicer quantity to consider is the max entropy, but where you put in some approximation to basically make it continuous. You take the you let yourself throw out very small eigenvalues of the state, and you minimize the rank over that process. So you consider the log of the rank of some other state, which is within epsilon distance of the original one in some appropriate measure, and you take the infimum. So one thing I want to say is that in information theory, the von Neumann entropy is useful, not in its own right, but mostly as a stand-in for the smooth max entropy or other so-called operational quantities that have a more direct interpretation. As an example, there's this very famous theorem, which is that it's the quantum version of Shannon's noisy coding theorem, which is that the von Neumann entropy and the smooth max entropy of any state agree in the limit as you take a large n number of copies of it. This is what's sometimes called an asymptotic equipartition theorem. It's called typicality. It's called the focusing on typical sequences. It has a lot of names. But this is why information theorists really care about the von Neumann entropy, because it's a stand-in for this other thing. This leads us to a definition that I think is going to be very useful for us to think about in gravity, which is compressibility. You say a state is compressible if its von Neumann entropy is a good approximation to its smooth max entropy, which is its effective degeneracy of microstates, and you say it's incompressible otherwise. This is a loose definition because I've said good approximation and I haven't told you what that means. Really, you have some parametrized family of states, and you ask whether these things have the same parametric scaling in a particular limit. So an example of a family of states that is compressible is this one I showed before. You have one very large eigenvalue of, say, size 1 minus 1 over n, and you have a bunch of very small eigenvalues. In the limit as n goes to infinity, the entropy and the smooth max entropy of this thing do go to 0 at the same rate. But an example of an incompressible spectrum is one that's like a geometric sequence. This is just some calculation you can do. It turns out that in the limit as you take the ratio to 0, this thing does focus in on a pure state, but the smooth max entropy and the von Neumann entropy are very bad approximations to each other. So it seems like a refined understanding of entropy in gravity will need to think about these smooth entropies and not just the von Neumann entropy. Prior work has studied these in the context of the Ryutaki-Yanagi formula. There was this work showing that sort of the standard gravitational path integral replicatrix states, the things where the Renyies are dominated by a permutation symmetric saddle, these things are compressible. But in a paper that was really influential for me and really formative, Akers and Pennington showed that there do exist non-compressible states in quantum gravity, states for which the von Neumann entropy does not compute an accurate counting of the degeneracy of states. These are funny things. These aren't black hole states. They're sort of funny states involving a lot of bulk matter, but nevertheless, they're things that require a refinement of the way we think about entropy. And indeed, these authors, along with Adam Levine and Liz Wildenhain, had a very nice paper last year talking about how to fix up the RT quantum extremal surface formula in that setting. So this work is very instructive, and it's, I think for me, one of the most influential things that's happened in the past few years. But one of the shortcomings is that it's doing a semi-classical analysis, but it's using very much microscopic ideas. And one thing that we can, I'm going to skip this slide. One thing that we can do is we can think about whether this technology from the first part of the talk, this sort of pure continuum semi-classical gravity language for talking about entropy, can give us a more refined understanding along those lines. So I just have 2 more quick slides. I'm going to tell you about a very almost trivial preliminary calculation that does suggest that these type 2 entropies that we talked about in the first part of the talk actually do tell us something about state counting. Okay. Yeah. Does what need gravity?
I mean, you're talking all the time about you're using the language of direct quantum theory, which applies and makes sense for theories, quantum theories that are
Yeah.
in the continuum.
Right.
What applies to gravity?
Okay, so the is sort of a technical point, but the structure, one of the points of this work is that you have algebraic tools for talking about pure quantum field theory in the continuum, and you have algebraic tools for talking about quantum field theory coupled to gravity, and the structure of those things is very different. So there are plenty of tools you can use to talk about continuum quantum field theory, and that's just a different set of questions than the set of questions you ask about quantum field theory coupled semi-classically to gravity. And that's the setting where these type 2 entropies show up. And they don't show up in pure quantum field theory without gravity as a coupling. Okay. Maybe let's revisit in a second. Let me just show these equations. So the thing in the second part of the talk, I tried to argue for you that we should care about these max entropies, which are these literal countings of the rank of a density matrix. These are things that literally count the number of microstates. And you could define them as the log of trace of density matrix to the power 0. That's the thing that is just the projector onto the support of the density matrix. It sets all of its non-zero eigenvalues equal to 1. So, because I've told you that there are these general algebraic settings in which we have traces, we might think that the thing we want to define in that setting is analogously log of renormalized trace, rho to the power 0. Of course, because of the scaling ambiguity in a general algebraic setting, we're only going to be able to consider this entropy difference, which is the log of the ratio of traces for 2 different states, the projectors onto their different supports. So a question I basically want to ask is there a sense in which semi-classical gravity tools can tell you that this has an interpretation as some sort of relative state counting, even without knowing microscopics? And the answer is yes. So for simplicity, let's just suppose that the ratio of these things is an integer. I'm going to tell you a theorem. I've never seen anyone write this down, but it follows from a paper that was written in 1937, so we certainly could have figured it out before. There exists, whenever you have this ratio of the traces being an integer, there always exists a unitary equivalence between the support of one of the states and the support of the other state, tensor an n-level quantum system. Okay, all of these Hilbert spaces are infinite dimensional, so the fact that a unitary equivalence exists is kind of trivial. Any 2 infinite dimensional Hilbert spaces have a unitary equivalence. But the crucial thing is you can actually show that the unitary operator that implements this is in the algebra that you have under consideration. Okay, it acts on the original Hilbert space tensor an extra factor, so it's in the algebra tensor some extra thing. But that is nevertheless a statement that these abstractly defined max entropies in these algebraic settings that showed up in semi-classical gravity, they do give you a statement about a relative state counting where you say that the amount of extra information you need to represent one state, conditioned on already having a representation of the other, is exactly this extra number of degrees of freedom encoded by this max entropy. So I guess just to summarize, we have this algebraic entropy difference formula, which is UV finite, and it gives us a really good playground that I don't think we've had before for understanding semi-classical entropy. Most of its properties are unknown. We don't even know if it reproduces the features we expect from a microscopic answer, but this preliminary result I just showed you shows that at least when you try to make the most naive connection possible to this quantum information theory literature, you end up with something that looks like state counting at the classical level, not an absolute state counting, crucially. That's something we can never expect to get from this analysis, but nevertheless a relative state counting. And I want to close, I was just reading Fermi's thermodynamics book last week for sort of unrelated reasons, but he made this point very clearly in his book when he was trying to sort of revisit classical statistical mechanics once he already knew quantum statistical mechanics, was to say, to really drive home this fact that classical statistical mechanics cannot lead to a determination of the entropy constant. Nevertheless, classical statistical mechanics are interesting. And that's the same perspective that I'm taking here. Classical or sort of semi-classical black hole physics is never going to be able to determine absolute entropies for us, but there's a lot more to classical statistical mechanics than we've managed to understand so far about semi-classical black hole entropies, and I think that's where we're pushing. Okay, thanks very much.
Questions?
So when you were discussing the mass, you used the word ADM a lot.
Oh yeah.
Is all this formalism specific to asymptotic flat space? Or?
No, not at all. I mean, I said ADM because it was easy. Flat space is easiest. Of course, if you have ADS space, then you need to choose boundary conditions, but we have our favorite boundary conditions. We choose the reflecting ones. And then you do have a good notion of a mass for a slice.
So the reason I ask is, can we try to sort of embed this in ADS CFT and then compare with actual microscopic?
That is how this first paper by Witten, that was the perspective that this first paper by Witten took. Right, so he was thinking specifically about how this structure might arise not from the semi-classical level, but rather from the large n limit of n equals 4 super Yang-Mills. And that is one way of getting the structure. You take the large n limit of super Yang-Mills and you find that some stuff happens to the Hamiltonian and it starts interacting with the single trace sector and stuff like this, and you end up with these type 2 algebras. I think that's very interesting. That's still something that could be explored further. I wanted to make the point here, as was made, not just by me, also by Witten and collaborators in a later paper, that this stuff can be done without knowing a microscopic description that you're taking the limit of.
But does the cross product have an interpretation?
Does the cross product have an interpretation? Yeah, it has to do with the fact that the appropriately rescaled Yang-Mills Hamiltonian is like h over n, and this thing commutes with the single trace sector in the infinite n limit, but when you add 1 over n corrections, it stops commuting, and that thing, you have to do a basis rotation to get it in this language, but that gives the cross product.
I have a completely different question. So in information theory, people have come up with sort of an infinite, you use the max entropy, but there's actually an infinite number of entropies.
Yeah, that's right.
Is there any sort of black hole or physics interpretation of this?
Yeah.
Yeah, those alphas are parameters, right? They're continuous parameters or sometimes discrete parameters.
Good. Yeah. So certainly papers have been written about this. I would say I don't really know what the state of the art is. There's a sense in which there is this family of entropies, but there's a sense in which, from an information theoretic perspective, the most interesting one are the max and the min, because these things have very clear interpretations. Well, the max has this microstate counting interpretation, the min has a slightly less transparent interpretation, and they sort of sandwich everything else. And one thing
in the large and limit.
Yeah, that's right. That's right. One thing that tends to happen is that when you start taking approximations, these things tend to like very seriously condense in on each other, and they all tend to become equal up to parametrically small quantities. That's this compressible situation. So the settings in which you might actually expect the different quantities to give you qualitatively different physics are these incompressible settings, and I think we really are just at the beginning of understanding those, so I don't have a sharp answer.
The reason I ask is because the differences are sensitive to 1 over n. So that might be interesting to
Yeah, absolutely. I mean, if you want to compute something like trace rho to the alpha microscopically and look at the whole spectrum of alphas, that's equivalent to knowing sort of the full eigenvalue spectrum of a black hole, right? So in some sense, if you declare that you're focusing on the microcanonical ensemble in the first place, then you already know all of those things because they're all the same.
So what I meant is that the language is a continuum. It's more like a 1 over n approximation rather than...
What language?
If you repeat what you did, historical black hole,
Yeah.
with other entities, same.
Oh, I see what you're saying. Yeah, so that's basically what I was trying to get at with this last part of the talk, is that these very last 2 slides were about telling you how to think about one of these entropies in this cross product context, and certainly there's much more that should be done to understand this better. Yeah.
It sounds like you're giving a state counting interpretation of the max entropy when the ratio of the 2 traces of rho to the 0 and sigma to the 0 is integer.
Yeah.
When it's not an integer, do you have anything?
Yeah, when it's an integer, there's like a remainder term. So if the ratio is like, 3.5, then you can represent this. You can represent this state as you can represent this space as this space tensored a qubit direct sum something else that is in some sense strictly smaller than this Hilbert space here. I mean, I would really just think of it as like one of these classic, I'm talking about tensoring on an additional degree of freedom, so in some sense, the really interesting thing is sort of the ceiling integer of whatever this quantity actually is, because that's the smallest quantum system I could actually tensor on and get this information. But in principle, there are formulas with these non-integer remainder terms. I just don't think they're very instructive.
Thank you.
Maybe related to Roberto's question, also Samir's question. I mean, isn't it somehow worth emphasizing that we did this semi-classically, and in the end, the fact that we got A over 4G was because we imposed the Einstein's equations in the bulk. Maybe just to make this sharper, if we go back to the discussion of the previous talk, where we expected a specific correction to the entropy, which we weren't getting just by imposing Einstein's equations. We needed. It's not that the type 2 language would somehow magically produce this for us, right? We don't expect it would do that unless we know.
No. No. I have no... there's a comment in Witten's first paper on this subject about logarithmic corrections, but I think that's actually been subsumed by things that we understand better now. Let me just comment, the interesting thing here is not just that you get A over 4G, it's that you get A over 4G plus SQFT, which is the Bekenstein-Hawking formula. Yeah, it's the particular combination of these things that is showing up that is interesting.
That's right. But for instance, if you wanted to ask if you'd get the Wald entropy or get high, you wouldn't get that unless you put in the corrected constraints.
You absolutely get Wald entropy if you put in a higher derivative.
But you have to put in the corrected constraints in the bulk.
Yeah, that's exactly right.
You get out what you put in.
You get out exactly what you put in. That's right. Yeah.
I think our time is up. So let's thank Jonathan.